In the last module, we left off with the tip or trick that you can tell if your binary number is odd or even depending upon the rightmost digit. If it's a 1, it's odd. If it's a 0, it's even. So let's go on and let's do a little bit of addition in binary. And let's start with the binary number, which would be the equivalent of 3. Analyzing it, we could see that the rightmost digit is a 1, which means it's an odd number. The placeholder of that one is a 1. The placeholder of the second one from the right is a 2, so 2 plus 1 is 3. So let's add 1. Now, remember the principle. Adding 1 to the highest number gets you 0, carry 1. So when we add 1 and 1, we get 0, carry 1. Now we have another 1 and 1, so that's going to be 0, carry 1. We now have 1 and 0, which is going to be a 1. And trust me, you get so goofy with this stuff, you go, 1 and 0 is 0, and 1 and 1 is 1. And it's very easy to mix these up because it's so mind-numbing to look at all those 1s and 0s. So do it carefully, double check it. But in this case, we don't have to carry anything, so everything else should just bring down 0s. And sure enough, if we use our placeholder idea, from the right, we have 1, 2, and 4. So the 1 turned on there is the value of 4. As an exercise, I would suggest that you start with the binary 1 and add 1 to it. And we have the answers on this next screen. You could practice adding 1 and see if you come up with the same numbers. In the older version of this PowerPoint that's available in Blackboard, you can find this slide and print it off so you could check the answers. Moving on. The short integer number is 16 bits. Here's an important point. The leftmost position is the sign, positive or negative. A 0 in the leftmost position is positive. A 1 in the leftmost position is negative. When you're analyzing the number, you gotta start with that first. Excuse me. Is it positive or negative? Well, the largest positive number, I hope this is fairly obvious, we have the 0 in the leftmost position and a whole bunch of 1s, and that is the equivalent of 32,767. Yeah, it's worth memorizing that number. On the other hand, the smallest negative number is a 1 in that position, followed by a whole bunch of 0s, and that is negative 32,768. Now, here's something we'll explain later, but the largest negative number has a 1 in the leftmost position, followed by a whole bunch of 1s. We'll talk about smaller and largest negative numbers later. How do you know what integer a negative value is? You cannot tell by looking at it or even adding up bit values like you could for positives. We have to do something called 2's complement, completing the 2's. The nice way of putting it is reverse the bits and add 1, but how many years ago has it been? 40, 35? My teacher said, flip the bits and add 1. All right, we're young and irreverent, right? So if I say flip the bits, pardon my French. But the good news is this works to find either the equivalent positive or negative number. Don't know why, it just does. Actually, somebody explained it to me mathematically and engineering-wise once, and I said, wow, that's interesting, and I got it for about 5 minutes. Here's an example. Let's start out with this negative number. How do I know it's negative? the one in the leftmost position. Let's flip the bits. The 1 becomes a 0. The 0 becomes a 1. The 1 becomes a 0. The 0 becomes a 1. The 0 becomes a 1. The 1 becomes a 0. And it's real easy to make a mistake here and forget to flip the rest of them. But obviously all the rest of these 1s are going to be 0s. Okay, so far? Make sure you understand why we came up with this number. Now let's go ahead and add 1. A suggestion when you're doing the exercise is somehow lightly mark out the original number. Not so bad that you can't see it, but enough that it's not going to get in the way, because people tend to bring it into this next step. This addition is going to be easy because we don't have any carrying. 0 and 1 is 1, 1 and 0 is 1, 0 and 0 is 0, 1 and 0 is 1, 1 and 0 is 1, and all the rest of them are zeros. Now I have the equivalent positive number. And if I count up the bit positions, see if you can do this in your head. 1, 2, nothing in 4, 8, and 16. So 1, 2, 8, and 16, that's a 27 in base 10. It would be a mistake to stop here because the number did not start out as a positive 27. It started out negative, so the final answer is the original number is a negative 27 in base 10. Let's go through the steps you might use to do the reverse. As I was preparing this lecture, I realized this is something I've never covered before. Maybe a good idea to do that. Let's take our previous example, the 27. How can I convert this back to binary? I'm just going to suggest the procedure, and you should try to figure it out yourself. What you do is find the largest binary number that will go into it as an integer value. It's a little bit of trial and error, actually. Except, if you did 64 integer division, you would get a 0 and it would work out okay. Just a suggestion. But in this case, 16 would be the largest because 32 is too large. So wherever the 16 bit is, that one would be turned on. And then you actually take mod. Take 27 mod 16, you get 11 in base 10. And then we would repeat the process. The largest binary number that will go into 11 is an 8. 11 mod 8 gives me a remainder of 3. The largest binary number that would go into 3 is a 2. 3 mod 2 gives me a 1. And we could figure out then the equivalent binary number. This will conclude this segment. Come back and we will work on a few more ideas here.